Yeah, thank you, Marius. My name is Peter Wirtz, and I'm a research associate for I think 4 months now. And as Mario said, before that, I wrote my master thesis at the market-based topics of the WP2 in the HydroFlex project. And during my work as research associate, I also presented and published a paper just last week at the European Energy Market Conference, which took place in Stockholm but was virtual. So I wasn't there, but we presented it last week. And I would like to show some market investigations today, where I would like to first motivate this market investigations. Then I will follow with an analysis and talking about a methodology, where I describe a two-step approach how to simulate highly complex hydraulic systems, which is needed to evaluate the demand for flexibility provided by hydropower. After that, I would like to show some exemplary investigations of our research work and close my part of the presentation with a summary. So first, I would like to show how hydraulic power plants are used nowadays, and therefore I randomly chose one hydraulic power plant in Sweden, which is named Bastusel. And as you can see on the right side of the slide, the number of start-stop cycles per day for the year 2018 for this Bastusel power plant varies all the time between 0 and 2 times. And this is an average about 0.5 start-stops per day, which is not very high. So hydraulic power plants are not used to provide a lot of flexibility today. And the result of this is that with each start-stop cycle, the technical aging is higher than without start-stops. And this raises the question which operational requirements hydraulic power plants have to meet in the future, and which future trends and developments do influence the flexibility provision by hydraulic power plants, and in particular this number of start-stop cycles. As Mario said in the introduction, the trends and developments in the European power system are going to differ significantly from today's European power system. So because of the higher shares of renewable energy sources, the more decentralized electricity generation, and the mothballing of conventional power plants, we do have a higher demand of flexibility in the future due to this higher forecasting errors and higher volatility in the generation power system, and also due to the different and higher loading of the grid. And as Mario said, that the conventional power plants which are used as flexibility options are not available in the future, and because of their more decommissioning. So now I'd like to answer the question, what exactly is flexibility in the power system? And flexibility describes is the potential to balance the generation and demand, because these needs to be equal all the time. And to provide this flexibility in the power system, there are existing different measures and technologies which are also varying in time and space that can provide flexibility. I would now like to go a little bit more in detail which options we do have to provide flexibility in the power system. And there we defined 4 different possibilities to provide flexibility. On the one hand, the adjustment of generation and the adjustment of demand, and on the other hand, by spatial coupling or by time coupling. The adjustment of generation is possible by regulating power plants in the future, and how it is done today too. Then the adjustment of demand could be made, for example, by demand side management, spatial coupling by with spatial coupling you can provide flexibility over longer distance, and the time coupling could be made by energy storages such as power to gas or batteries. And this, for different possibilities, might change in the future. So due to the decommissioning of conventional power plants and the higher shares of renewable energy sources, the adjustment of generation might be not as big as a flexibility provider as it is today, and therefore, for example, the adjustment of demand might play a bigger role in the future with demand side management, which may become more and more important in the future, but is currently not widely used. Spatial coupling, by spatial coupling due to the higher shares of renewable energy sources, this tends to an increasing load of the grid, and by grid expansions in the European grids, this could be another flexibility provider. Also, the energy storages to provide time coupling flexibility are getting more and more important because of the higher shares of intermittent renewable energy sources. Furthermore, all these different possibilities are relevant in order to evaluate hydraulic systems, because a hydraulic system can provide 3 out of these 4 possibilities. The adjustment of generation could be made by storage power plant. Also, the adjustment of demand is possible by pumped storage power plant, and the time coupling also in general because of the storage of hydraulic storage power plants. So in order to evaluate these hydraulic systems, I would now like to show present our methodology to simulate highly complex hydraulic systems in order to see the demand for flexibility in the future. And this methodology, this approach is divided into 2 steps. On the one hand, a fundamental market simulation, and on the other hand, a hydropower plant commitment model. The market simulation already exists at our institute and needs several input data, such as power plant parks, net transfer capacities, rest time series, primary energy prices, demand time series, and bidding zones. And the objective of the market simulation is to minimize the overall electricity costs, generation costs. In this process step, the hydropower of highly interconnected and therefore highly complex hydraulic power plant parks are considered in an aggregated form, as well as the time resolution is set to an hourly resolution, and these 2 types are made to reduce the computing time of this very complex simulation. Yes, and the result of this market simulation is that you get the feed-in time series, power exchanges, reservoir level, etc. from this market simulation. The result from this first process step is used as an input data for the second process step, this hydropower plant commitment model. And there we used the aggregated feed-in time series from the previously aggregated hydraulic power plants as input data in this model. This model includes a rule-based algorithm, which objective is the efficient use of the available water by considering technical restrictions. In this process step, the hydropower, which was aggregated in the first step, is now viewed in detail, and the time resolution is set to a quarter-hourly resolution. As a result, we get the detailed feed-in time series for every single hydropower plant with a quarter-hourly time resolution. I would now like to focus a little bit more on this second process step, this hydropower plant commitment model, which is divided into 3 parts. The data preparation, parameterization of the hydropower plants, and the rule-based algorithm, which can simulate the feed-ins time series of the hydropower plants, which is the main part of this model. First, in the data preparation, the objective is to get the same time resolution as it is in the intraday market. So to interpolate the input data, which are in an hourly time resolution, to a quarter-hourly time resolution and to quarterly time resolution. There you need to keep in mind that if a volatile time series, like from wind turbines, is interpolated, for example, linearly or by a spline interpolation, this time series would lose its original volatility. So therefore, within the framework of our research work, we developed a method to interpolate volatile time series without losing their volatility. To do that, we added a stochastic roughness between the hourly points of the time series, and this roughness is based on historical volatilities and data. So how that could look like is shown in the figure below at the bottom of the slide. In the blue line represents the hourly time resolution, is just an example, and the orange line represents the new volatile interpolated time series. To achieve that the energy balance stays the same all the time, these added volatilities are compensated by flexibility providing technologies. In the second step of our hydropower plant commitment model, the parameterization of hydropower plants is made. With this parameterization, we parameterize the minimum up and down times of the hydropower plants to depict their flexibility. By that, we categorize the hydropower plants into two different classes. On the one hand, flexible systems without a minimum up and down time, and inflexible systems with one defined minimum up and down time. These flexible plants can be chosen by different criteria, but I will come to that later in the exemplary investigations when we really choose the flexibilized units. So next, the rule-based algorithm for each time step in our simulation, the feed-ins for the hydropower plants is calculated until the load is covered. So first, in each time step, the turbines whose minimum uptime has not yet been reached are selected. This is made to avoid operational violations by the hydropower plants. And this is followed by a short time forecast to detect load fluctuations, so that we know how many flexible and inflexible plants do we need to cover the peak and the base load. And this pre-selection of the more flexible and inflexible turbines based on this forecasting is made in the third step. Then after this pre-selection, the most efficient turbines at the optimum operating point are chosen for each time step. In this selection, the minimum downtime of every turbine is also considered so that there are no operational violations. The algorithm ends when all load in all time step is covered. I would now like to focus a little bit more on this third step, this pre-selection of the more flexible and inflexible turbines. There we, T0 in this figure describes the point where the feed-ins need to be calculated. The difference T1 minus T0 describes the forecast duration time at this process step. And then the minimum and maximum in this forecast horizon is calculated to know what the peak load is and what the base load is of this process step. Then the flexible plants are chosen to cover the peak load, and if the capacity of the flexible plants does not reach the capacity of the peak load as it is shown here in case 1, also inflexible plants are taken to cover the peak load. Furthermore, if the capacity of the flexible plants is higher than the peak load, then the peak load is completely covered by the flexible plants. For the base load, the most efficient flexible plants, which are not yet in use for covering the peak load, and the inflexible plants are used to cover this base load. After the presentation of our methodology, how to simulate highly complex hydraulic systems in the future, I would now like to continue with our investigation plan and our exemplary investigations. On the left side, you see that the market simulation's spatial scope is the European region, but there the hydraulic systems in the Nordics, like in Norway and Sweden, are considered in aggregated form to reduce their complexity, as I said in the methodology. And in the second process step, the hydropower plant commitment model, the previously aggregated hydraulic systems are now viewed in detail. It is noticeable in this graph that we divide the country Norway into two different market areas, Norway or NO and Norway South or NOS. As input data, we chose 3 different scenarios, which already has been defined in the framework of the HydroFlex project, as Mario said in the beginning. And therefore, I would just compare them qualitatively in order to show the main differences between these 3 scenarios. So we considered that the reference scenario is the most probable scenario, and then we also considered a green hydro scenario and a prosumer scenario, all 3 for the years 2030 and 2040. In addition to that, we looked at the reference scenario in 2000. We defined a reference scenario for 2025, but because of not that big uncertainties at that point, we only defined 1 scenario for this time point. So the main difference between the scenarios is set in the amount of PV units and wind turbines. And in this table, the qualitative difference between the scenarios is carried out. In this table, the reference scenario for 2030 is used as a reference. And from there, you can see that the prosumer scenario, in the prosumer scenario, more PV units are expected in the year 2030. And in the green hydro scenario, both more PV units and more wind turbines are expected in comparison to the reference scenario. From the year 2030 to the year 2040, in all scenarios, the number of PV units and wind turbines will increase. In our second process step, this hydropower plant commitment model, we considered all hydraulic storage power plants above 10 megawatts. This corresponds to about 9 gigawatt capacity in Norway or NO, 20 gigawatts in NO South, and 12.4 gigawatts in Sweden. We set the minimum up and down time of the flexible units to 0 hours and of the inflexible units to 2 hours. So now the question arises, which units should be flexibilized in our investigation? Therefore, we did some preparatory investigations where we compared different flexibilization rates and different flexibilization criteria. The criteria could, for example, be that we only flexibilize the most efficient turbines or the most inefficient ones, or the biggest, the smallest, or the oldest, or also the ones with the most violations of operational violations from previous investigations. As evaluation parameter, we used the overall water consumption, so that the to achieve optimal economic use, and also the average number of start-stop cycles of the flexible units, because if this one is higher, the optimal use of the flexible units are guaranteed. So in this figure is the result for these two parameters is shown for the different flexibilization rates. And what is noticeable in this graph is that the more units are flexibilized, the fewer start-stop cycles, average start-stop cycles the flexible units have. And this can be explained because if the rate is higher, then more and more flexible units are used to cover the baseload, and this results in decreasing number of start-stop cycles of the overall flexible units. Furthermore, the most start-stop cycles of the flexible units and the low water consumption is best when we only flexibilize the 5 reference sites from the HydroFlex project, which is shown here on the right. It is possible to flexibilize more than these turbines, and with this we can reduce more operational violations. This need to keep in mind. So for the further investigations, we decided to only flexibilize the reference sites. So now the question arises, which flexibility demand must all of the hydropower plants in a market area meet in which scenario? And therefore, we compared for the different scenarios and market areas the number of operating point adjustments of the aggregated feed-in time series from the market simulation, so from the first process step. And we assumed that the number of operating point adjustment of this time series is a measure for the demand for flexibility in this market area and scenario. And as it can be seen in this figure on the right, the number of operating point adjustments per year are all about 700 to 1,100, which is for one day only 2 to 3 changes per operating point adjustments per day, which is not very much. So this asks us the question why that the flexibility demand in the future might be not as high as expected. Furthermore, in this figure, we see that within the further the year of consideration is, the higher the operating point adjustments are. This, and also that the market area Sweden and the scenario green hydro, in this scenario the number of operating points are very high, and this corresponds to their higher share of wind turbines in comparison to the other scenarios and market areas. So next we would like to answer the question, how flexibly then will individual unit be operated in the future when the demand for flexibility is not as high in this investigation. And therefore, we compared the number of start-stop cycles of the hydropower plants for the year 2030 for each scenario. One here on the right side, you see these number of start-stop cycles on the one hand for the flexible turbines, so for the reference sites, and the inflexible turbines. And it is noticeable that the number of start-stop cycles of the flexible units is much higher than of the inflexible units, because these are used generally to cover the peak load. Furthermore, it is noticeable that in Norway, so in the market area NO, the number of start-stop cycles of the flexible plants is higher than in the other market areas. And this is the result of, this can be explained because in this market area, only one reference size is, there's only one reference size, and this reference size, which is called Wirtz, need to cover all the demand fluctuations, and therefore is higher than in the others. But it is also noticeable that the number of start-stop cycles of the flexible units in the market area Norway South is lowest in comparison to the others. And this arises the question which the difference between the market area causes, which the causes are for this these differences. And this needs a deeper look into the time series itself. So therefore, on the right side, we plotted the aggregated time series, so of the hydraulic power plants of Norway and Norway South in a 10-day frame for the prosumer scenario 2040, because this is the one with the highest amount of PV units in Central Europe. And also in this plot, the aggregated time series of PV feed-ins from Germany is shown. And this graph shows that there is a big influence from the PV units generation from Germany to the generation of hydraulic power plants from Norway, because every time when the generation from the PV units from Germany is high, the one from hydropower in the Nordics is low, and the other way around. This dependency from the PV units from Germany is also seeable in this graph below that, where the net exchanges from Norway South to Germany is shown. And as you can see, this net exchange is almost all the time fully utilized. So the capacities are always full, and this is the reason because of high price spreads between Germany and Norway, because of their very different power plant park structure. So in the Nordics, we have a lot of hydropower, and in Germany, a lot of wind and PV. And now with this investigation, the question arises, what is with the other bidding zones around Norway? So what is with the Netherlands and UK and Central Europe? And to explain this, this influence of the net exchanges from all neighbors, on the right side, the annual duration cost of the net exchanges from Norway to all other neighboring market areas are shown. So the annual duration costs represent the values of the net exchanges in a descending order over 1 year. So there's also the annual duration curve from Norway South to Germany shown in this graph, and this behaves the same way as the annual duration curve from Norway South to the UK, Netherlands, and Denmark, because in almost, I would say, 10 out of 12 months, the net transfer capacity is fully utilized in 10 out of 12 months. And this also shows that this is also the result of the high price spreads between Norway and let's say Central Europe. In this figure, it is also noticeable that the net exchange from Norway South to Norway itself, so to the north, and to Sweden is not fully utilized all the time, and most of the time stays around 0. And this leads to this is the reason, because the power plant parks are very similar with a lot of hydro, and there are smaller price spreads within these areas, which leads to the result that a higher demand for flexibility in terms of several start-stop cycles a day are more likely to be expected in the Nordic region itself than from Central Europe. So then we made a sensitivity analysis because of the previous investigation result that the share of wind turbines might influence the demand for flexibility in the market areas in Norway and Sweden. We made a sensitivity analysis with a maximum start-stop cycle scenario, we called it like this, where we took the green hydro scenario for 2040 as a basis, but increased the capacity of the wind share in Norway from 10.4 gigawatt in the green hydro scenario to 28 gigawatts capacity in this sensitivity scenario, to see how the flexible and inflexible units would operate with this scenario. And therefore, on the right side, again, we see the box plots with the number of start-stop cycles per year for the flexible and for the inflexible plants. And there you see that the maximum number of start-stop cycles is only increasing in the market area and also in the north of Norway with this one hydropower plant, and this result leads us to the conclusion that only the high wind shares results in a higher demand of flexibility when the influence of the power generation from PV units from Central Europe, as I showed before, is only moderate. So in the north, we don't have this influence as much as we have in the south, and therefore the demand for flexibility in the north is higher than in the south. And with this maximum start-stop cycle scenarios, we came to up to 11 start-stop cycles per day for this flexible turbine in this scenario. And lastly, I would like to show why why despite this flexibility, not as high flexibility demand as we expected, it is still there are still a lot of benefits to install the new turbine technology, and therefore to see what additional benefits flexibilization can have. We started a simulation one time with the flexibilization of the reference sites and one time without any flexibilization. As you can see here on the left side, we plotted the number of operational violations of the inflexible turbines, and this can be reduced by about 66% if we flexibilize only the reference sites. And furthermore, on the right side, the average number of start-stop cycles per year for the inflexible turbines is shown in blue for the case without any flexibilization, and in orange with the flexibilization. And also here you can see that with the flexibilization, the number of start-stop cycles of the inflexible turbines can be reduced by up to 11%. And both the operational violations and the number of start-stop cycles leads to a faster technical aging of the turbines. We can conclude that a flexibilization of this reference site will slow down the technical aging of the inflexible units in this market area. So let's summarize our market investigations and research work. And so as we said in the beginning, there are future trends and developments expected in the European power system that could result in a higher demand of flexibility. This raises the question which operational requirements hydraulic power plants have to meet in the future, and which future trends and developments do influence the flexibility provision by hydraulic plants, in particular by the number of start-stop cycles. The simulations show that there will be a slightly higher demand for flexibility in the future European energy scenarios, but the electricity generation from PV units in Central Europe will have a significant influence on the hydropower operation. Furthermore, with the transmission capacities from the Nordics to Central Europe will be mostly fully utilized by this electricity generation from PV units and the Nordic hydropower, which is made because of the high price spreads between these market areas. This leads to a higher flexibility demands in terms of this leads to the conclusion that there only might be higher flexibility demands in terms of several start-stop cycles of the flexible turbines, more in the Nordic region itself than from Central Europe. Additional to that, we started a sensitivity analysis where we showed max start-stop cycle scenarios, and there we have seen that when with a higher share of wind in Norway and Sweden, we can achieve up to 11 start-stops per day for the flexible plants. An additional benefit of the flexibilization of the reference site is that the technical aging of the inflexible units could be slowed down a little bit. Yeah, thank you for your attention. This was my talk about the market investigations. I'm open for questions now.
Yes, thank you very much, Peter. So before we go on to Mike, let's open up if there is some questions directly related to the presentation that we've heard. Of course, we'll have a discussion afterwards, but if there's any specific clarification that is needed, you can either use the chat function or we will try to open up so people can grab the word.
Yes. Okay.
Hello, this is Niklas Dahlbeck in Sweden.
Yeah.
Can you hear me?
Yeah, I hear you.
Question, as your result, you have the power transmission line go fully and change like 10 hours apart. So what is the definition of it? You had a start-up time bigger than 2 hours. And if you know that it will be 10 hours time running, you can start up cascades. So that means that you can involve even more units. So what is the definition of inflexibility and flexibility in that case?
So we chose, like, for simplification reasons, only one minimum up and down time for the inflexible units, which we set to 2 hours. You can also set them to 10 or also use different minimum up and down times for the inflexible turbines. And then there might be other results, so that we might have more operational violations when we set this time to maybe 10 hours, because the inflexible turbines then are more inflexible than the ones we are considering right now, and then they really can only be used for the base load when they have such high minimum up and down times, so that we might need more flexible plants, like a higher flexibilization, not only the reference sites, to be able to cover the peak load all the time. I don't know if I answer your questions, or Is there any other question?
And Niklas, did you get? Are you happy with the answer or?
I'm not sure if I followed all the way, but I see what is getting at. Yeah.
But from my side, I follow. Sorry, go ahead, Niklas.
May I still pose another question, and that is when you talk about flexibility, we have many type of flexibility, different time scales, and you have focused on the intraday to some days in this when you're talking about this, but it means that many of the units are used for flexibility for shorter time scales. They are occupied with frequency regulation, so on. That means that not all is available for this.
Yeah.
So is that something you considered?
In the market simulation, we didn't consider that, but I think that this topic will be answered in the next part of the webinar, where we talk a little bit more about stability when Mike talks about this a little bit more. I think this would answer your question a little bit better, because in the market simulation, we only looked at the intraday market, day-ahead market, and not the frequency stability.
Okay.
Just a follow-up question regarding this figure, Peter. The interconnectors that you are considering, is that the situation today, or do you include the investment plans that the different transmission companies are considering or discussing about or planning?
I think in this because we are looking at the year 2030 and 2040, we considered the ones that are planned until that point. So from all interconnectors we know, we considered then until 2030, we considered the interconnections until then.
Thanks. Other questions?
There's one question in the chat.
Yeah, so there is a question in the chat if it is mainly focused in the results on the start-stop. But it's a question if you analyzed also the number of operating point adjustments.
Yes, exactly. So we, in this kind of investigation, we only looked at the start-stop cycles and not the operating point adjustments. This might need further investigations to do so, but to cope all our results from these different scenarios, and we have a lot of results. To cope all these, we just focused on the start-stop cycles because the main objective of the HydroFlex power was that how many start-stop cycles do we need for the hydraulic turbine, or is expected in the future, and so we focused on the start-stop cycles within our investigation.
Yeah, just for recalling for the audience who is not maybe as familiar with the HydroFlex project, so part of the call from the European Union was to look at the development of hydropower technology that would permit up to 30 start-stop per day and increase ramping rates. So that's the, let's say, the baseline that was in the call from the European Union, and that was the baseline for this project when we started up. Yes, the second question is the flexibility is based on the start-stop cycles. Yes, or at least this is used in this as a metric for the flexibility, I guess. Yeah.
But maybe to add at that point, Peter, if you could go a few slides earlier, I think we've shown the power adjustments. operating point adjustments derived from the first step of our tool chain. Yeah. Maybe this could be a maximum estimation of the operating point adjustment you could expect in the different market areas, Norway South and Sweden, because our second step, the hydropower unit commitment model, is based on this input data. So that could be a maximum estimate for the operating point adjustment. And yeah, it's around 600, 700 or up to 1,000 operating point adjustments per year. So breaking that down to days, we are talking about 3 or 4 operating point adjustments per day. So yeah, focusing on operating point adjustments, I think wouldn't increase the number or the amount of flexibility needed from the day ahead and intraday market perspective.
Thanks, Marius. So if there is no more questions, I will suggest that we'll give on to Mike Schoenfelder.